Today we will discuss Sylows theorem for finite abelian group. So theorem का statement देखते हैं. Sylows theorem for finite abelian group. इसका statement है if G is finite abelian group, P is a prime number such that P alpha is a divisor of order of G, but P alpha plus 1 is not a divisor of order of G, then G has a subgroup of order P alpha. इसका प्रूव है इफ alpha n is equal to 0, the obviously E is a subgroup of G and order of E is equal to 1. Then in this case the theorem is trivially true. Now suppose if alpha does not equal to 0 but P is a divisor of order of G, then by Cauchy's theorem for finite abelian group there exists an element A is not equal to E of G such that A to the power P is equal to E. Let S is equal to X belongs to G such that X to the power P to the power N is equal to E for some integer N. So A to the power P to the power A P dash is equal to E and A belongs to S. Let A is not equal to E, thus S is not equal to E. Therefore G is finite and so S is also finite. Thus to such that S is a subgroup of G, it is sufficient to show that S is closed. Let x comma y belongs to S, then x to the power p to the power n is equal to E and y to the power p to the power m is equal to E. So xy to the power p to the power n plus m is equal to x to the power p to the power n plus m dot y to the power p to the power n plus m. Since A is abelian, so E dot E is equal to E. Now xy belongs to S. S is closed and S is a subgroup of G. Let order of S is equal to P to the power B when P to the power beta when 0 is less than equal to beta is less than equal to alpha. If Q is any other prime number different from P is that Q is not equal to P such that Q is a divisor of order of S. By Cauchy's theorem and finite abelian group of an element C belongs to S such that C is not equal to E and C to the power Q is equal to E. Also C to the power P to the power N is equal to E for C belongs to S. Obviously P to the power N and Q are relatively prime by theorem lambda A plus mu B is equal to 1. There exist lambda and mu integers such that lambda P to the power N plus mu Q is equal to 1. Now C is equal to C dash which is equal to C lambda P to the power N plus mu Q. So C to the power lambda P to the power N dot C mu Q. So C to the power P to the power N to the power lambda dot C Q mu. So C is equal to E to the power lambda dot E to the power mu which is equal to E dot E. So it can be written as E. But C is not equal to E, which is contradiction. Then there exists number of prime order than P which divides order of H. Now let beta is less than alpha. G is abelian group and S is a subgroup of G. Then G is a divisor of S is also abelian. Order of uh, G by S is equal to order of G by order of S is equal to order of G G is finite, and so G by S is also finite. Since P is a divisor of order of G, and so P is a divisor of order of G is a divisor of order of S, is that P is the divisor of order of G by S. By Cauchy theorem, the finite abelian group, there exists Sx belongs to G by S, such that Sx does not equal to S, and Sx to the power P to the power n is equal to S. Sx to the power P, Sn to the power P, and so on up to n times. So S dot S up to n times. So here Sx to the power P to the power n is equal to S. So Sx to the power P to the power n is equal to Sn comma Sn plus so on up to Pn times. So S to the power Sx P to the power n is equal to X. So X to the power P to the power n is equal to S. By corollary of Lagrange theorem, A belongs to G, then A to the power order of G is equal to E. So it can be written as X P to the power n to the power order of S is equal to E. So X to the power P to the power n is to the power P to the power beta is equal to E. So X P to the power n plus beta is equal to E. Now X belongs to S by definition of S. Sx is equal to S, beta is less than alpha is not possible, so beta is equal to alpha. So here we can write order of S is equal to P to the power alpha, hence proved.